the teams I've seen be really successful at deploying ML products, they've had people who formally or informally have taken on that hot responsibility for the whole thing and kind of have the people who are writing the inner loops of the assembly kind of sitting next to the people who are, creating the models.
You're listening to Gradient Descent, a show about machine learning in the real world, and I'm your host, Lucas Bewald. This is a conversation with Pete Warden, well-known hacker and blogger. Among many things that he's done in his life, he started a company, Jetpack, which was a very early mobile machine learning app company that was bought by Google in 2014. He's also been a tech lead and staff engineer on the TensorFlow team since then. So he's been at TensorFlow since the very beginning. And he's written a book about taking ML models and making them work on embedded devices, everything from an Arduino to a Raspberry Pi. And it's something that I'm really passionate about, so we really get into it in the technical details. I think you'll really enjoy this interview. Quick disclaimer for this conversation. We had a few glitches in the audio, which are entirely my fault. I've been traveling with my family to Big Sur, which is a lot of fun, but I didn't bring all my podcasting gear, as you can probably see. And so if anything's inaudible, please check the transcription, which is provided in the notes. All right, Pete, so I have a lot of questions for you, but since this is my show, I'm going to start with the question that I would want to ask if I was listening to this. Which is, tell me again about the time that you hacked the Raspberry Pi to train neural nets with the GPU.
Oh, God. Yeah, that was really fun. So back when the Raspberry Pi first came out, it had a GPU in it, but it wasn't a GPU you could do anything useful with. Because, unless you just want to draw things, and who wants to just draw things with a GPU? But there was some reverse engineering that had been happening, and some crazy sort of engineers out there on the hardware side who'd actually managed to get a manual describing how to use how to program the Raspberry Pi GPU at a low level. And this had been driving me crazy ever since I'd been at Apple years ago, because I was always able to use like GLSL and all of these comparatively high-level languages to program GPUs. But I was always trying to get them to do things that the designers hadn't intended. Like when I was at Apple, I was trying to get them to do sort of image processing rather than just doing, straightforward graphics. And I never... You may hear a dog in the background. That is our new puppy, Nutmeg. But I always wanted to be able to program them. I knew that there was an assembler level that I could program them at if I only had access. And I spent 5 years at Apple trying to persuade like ATI and NVIDIA to give me access. And I actually managed to persuade them, but then the driver people at Apple were like, no, don't give him access, because then we'll have to support the crazy things he's doing. So when the Raspberry Pi came along...
And this is Raspberry Pi 1 or 2 or 3?
This was like back in the Raspberry Pi 1 days. So it was, not long after it had first come out. And they actually gave you the datasheet for the GPU, which described the instruction format for programming all of these weird little hardware blocks that were inside the GPU. And there really wasn't anything like an assembler. There wasn't, basically anything that you would expect to be able to use. All you had was the raw, like, hey, these are the machine code instructions. And especially back in those days, in the Raspberry Pi 1 days, there wasn't even any SIMD instructions really on the Raspberry Pi, because it was using an ARM v6.
Okay, I'm like nodding. What is a SIMD instruction?
Oh, sorry, single input, multiple data. So if you're familiar with x86, it's things like SEE or AVX. It's basically a way of saying, hey, I've got an array of, 32 numbers, multiply them all. And specifying that in like one instruction versus having a loop that goes through all 32 instructions and does them one at a time. So it's a really nice way of kind of speeding up anything that's doing a lot of number crunching, whether it's graphics or whether it's, in our case, machine learning. And I really wanted to get some cool image recognition stuff. This is back when AlexNet was all the rage. I wanted to get AlexNet running in less than like 30 seconds a frame on this Raspberry Pi. And the ARM v6 really was. It was like I think it was just like Broadcom had some dumpster full of like these chips they couldn't sell because they were so old. This is not official. I have no idea if this is true, but it feels true. And so they were like, "Oh, sure, use them for this, whatever this Raspberry Pi thing that we're thinking about." And they were so old that it was actually really hard to even find like compiler support. They didn't have, especially these kinds of modern optimizations that you would expect to have. But I knew that this GPU could potentially do what I wanted. So I spent some time with the data sheet. There were a bunch of like handful of people doing the open source hacking on this stuff. So I was able to kind of, fork some of their projects. Actually, funnily enough, some of the Raspberry Pi, sort of founders were actually very interested in this too. So I ended up kind of hacking away and managed to figure out how to do this sort of matrix multiplication. And that, funnily enough, one of the people who was really into this was actually Evan Upton, so the founder of Raspberry Pi. So he was actually one of the few people who actually replied on the forums when I was like sending out like distress signals when I was getting stuck on stuff. So anyway, I ended up being able to use the GPU to do this matrix multiplication, so I could actually run like AlexNet to recognize a cat or a dog in like 2 seconds rather than 30 seconds. So, and it was some of the most fun I've had in like years, because it really was just like trying to string things together with like sticky tape and chicken wire. And I had a blast.
How does it even work? Like, you're writing assembly and like running it on a GPU. Like what environment are you writing this in?
So I was just pretty much using a text editor, and then there were a couple of different people had done some work on assembly projects. None of them really worked, or they didn't work for what I needed. So I ended up sort of hacking them up together. So I'd then feed in the text into the assembler, which would produce the raw kind of command streams. And then I had to figure out the right memory addresses to kind of write to from the Raspberry Pi CPU to like upload this program. And then that program would be sitting there I think there was something like, some ridiculously small number of instructions. I could run like 64 instructions in there or something, or 128. The program would be sitting there on all of these. I think there was like 4 or 8 cores. I would then have to like kick them off. I'd have to like feed in the memory from and it was, I mean, honestly, it was like, if in terms of software engineering, it was a disaster, but it worked.
Well, like, what kind of like debugging messages do you get? I mean, I'm thinking back to college and writing this. I remember the computer would just crash, I think, when there was like invalid.
Well, I was actually writing out to a pixel, so I could tell by the pixel color how far through the program that it had actually got, which I'm colorblind, so that didn't help. But But yeah, it was really like getting down and dirty. It was the sort of thing where you can just like lose yourself for a few weeks in some really obscure technical problems. And
I mean, having worked on projects kind of like that, how did you maintain hope that the project would finish in a way that it would work? I think that might be the hardest thing for me to do, working on something like that.
well, at the time I was working on a startup, and this seemed a much more tractable problem than all of the other things I was dealing with at the startup. So it was, in a lot of ways, it was just it was procrastination on dealing with worse problems. So
Great answer.
yeah.
And I guess what was the reason that the Raspberry Pi included this GPU that they wouldn't actually let you like directly access? Was this for like streaming video or something?
Yeah, it really was designed for like I think early 2000s set-top boxes and things. So it was sort of, you were going to be able to draw like a few triangles, and but you weren't going to be able to run any, like, it wasn't designed to run any shaders or anything on it. So GLSL and things like that weren't even like considered like for it at that time. I think there's been some work on that since. I think maybe with some more modern versions of the GPUs. But back in the Raspberry Pi 1 days, it was just like, no, you're going to draw some triangles, and that's.
Have you been following the Raspberry Pi since? Like, do you have thoughts on the 4? And did they talk to you about what to include there? Maybe.
No. I think they knew better than, because I'm not exactly an average user. I mean, as a sort of a general developer, it's like fantastic because the Raspberry Pi 4 is this like beast of a machine with like multi-threading, and it's got those SIMD instructions I talked about. Like, there's, I think, support for GLSL and all these modern OpenGL things in the GPU. But as kind of a hacker, I'm like, oh, it's just kind of yeah, it's all kind of, so that, yeah, that's exactly.
Well, it's funny because I think I met you when I was trying to get TensorFlow to run on the Raspberry Pi 3, which is like literally just trying to like compile it and like link in the proper libraries. And I remember completely getting stuck. I mean, I'm ashamed to tell you that, and reaching out to the forums and being like, wow, the tech support from TensorFlow is unbelievably good that it's answering my questions.
Well, I think you ended up, you found my email address as well. I think you dropped me an email, and again, I think you caught me in the middle of procrastinating on something that I was supposed to be doing, and I was like, oh wow, this is way more fun. let me spend some time on this. But no, I mean, you shouldn't underestimate that. Like, TensorFlow has so many dependencies, which is pretty normal for like a Python sort of cloud server sort of project, because they're essentially kind of free in that environment. You just do like a pip install or something, and it all just works. But as soon as you're moving over to something that's not the vanilla sort of x86 Linux environment that it's expecting, you suddenly sort of have to pay the price of trying to figure out all of these, where did this come from?
Right. So I guess one question that comes to mind for me that I don't know if you feel like it's a fair question for you to answer, but I'd love your thoughts on it is, it seems like everyone trains their models, except for people at Google, train their models on NVIDIA GPUs. And, I'm told that's because of the CUDA library that like essentially like compiles the code, and CUDA-NN that kind of makes a low-level language for writing ML components and then, compiling them onto the NVIDIA chip. But, if Pete Warden can just like, directly write code to do matrix multiplication on like a chip that's not even trying to like publish its docs and let anyone do this. Where's the disconnect? Like, why don't we see more chips being used for compiling? Why doesn't TensorFlow work better on top of more different kinds of architecture? Like, I know that was one of the original design goals of TensorFlow, but we haven't seen maybe the explosion of different GPU architectures that I think we might have been expecting back in like 2016, 2017.
Yeah, and I can't speak so directly to the TensorFlow experience, but I can say more generally, um, what I seen happening, speaking personally, is it's the damn researchers. They keep coming up with new techniques and better ways of training models. And what generally tends to happen is it follows the same um, model that sort of Alex Krzyzewski originally did and his colleagues with AlexNet, where the thing that blew me away when I first started getting into deep learning was, Alex had made his code available, and he had not only been working at the high level model creation side, he'd also been really hacking on the CUDA um, kernels to run on the GPU to get stuff running fast enough. So it was this really interesting having to kind of understand all these high level concepts, these cutting edge concepts of machine learning, while also being this, in a loop kind of assembly, essentially, not quite down to that level, but like intrinsic sort of, really thinking about every cycle. Um, and what has tended to happen is that as new techniques have come in, the researchers tend to just for their own to run their own experiments, they have to write things that run as fast as possible. So they've had to learn how to, the default for this is CUDA. So you end up with, new techniques coming in as CUDA implementations. Usually there's a C++ CPU implementation that may or may not be particularly optimized, and then there's definitely a CUDA implementation. And then the techniques that actually catch on, the rest of the world kind of has to then figure out how to take what's often, great code for its purpose, but is written by researchers for research purposes, and then figure out how to port it to different systems, with different precisions. And there's this whole, um, hidden sort of amount of work that people have to do to take all of these emerging techniques and get them running across all architectures. And I think that's true across across the whole ecosystem. And it's one of the reasons that I really love for experimenting if you're in the Raspberry Pi sort of form factor, but you can afford to be burning like 10 watts of power. Grab a Jetson or Jetson Nano or something, because then you've got essentially the same GPU that you'd be running in a desktop machine, but just on a much smaller form factor.
Totally, yeah. It makes me a little sad that the Raspberry Pi doesn't have an NVIDIA chip on it.
The heatsink alone would be.
One thing I noticed. So your book is excellent on kind of embedded ML. And actually, I was in a different interview, which we should pull that clip of interview with Pete Skolmarek, and we both had your book on our desk. So we had reading it. I don't know if you know him, but
Yeah, no, I'm a good Pete's awesome. He's been doing some amazing stuff too. He's another person who occasionally catches me when I'm procrastinating, and I'm able to offer some advice, and vice versa.
nice. Maybe we should have a neighborhood.
Yeah, hacking procrastination list.
But I guess it seems like pretty obvious that you do some interesting projects in your house or for personal stuff. I was wondering if you could talk about any of your own kind of personal ML hack projects.
Oh, that's a really so I'm obsessed with actually trying to get a magic wand working well.
Okay, tell me more.
One of the things that I get to see is with these like applications that are being produced by industry professionals for things like Android's phones, smartphones in general, and the gesture recognition using accelerometers just works really well on these phones. And because people are able to get it working really well in the commercial realm, but I haven't seen that many examples of it actually working well, as open source or way. And, even the example that we ship with TensorFlow Lite Micro is not good enough. Like it's a proof of concept, but it doesn't work nearly as well as I want. So I have been, sort of that's been one of my main projects I keep coming back to is, okay, how can I actually, just sort of do a sort of, Zorro sign or something holding, I've got the little Arduino on my desk here and sort of, do that and have it recognize, I want to be able to sort of, do that to the TV screen and have it like change channels or something. And so what I really want to be able to do, we actually released some of this stuff as part of Google I/O, so I'll share a link. Maybe you can put in the description afterwards. But my end goal, because these things actually have Bluetooth, I want it to be able to emulate a keyboard or a mouse or a gamepad controller, and actually be able to sort of customize it so that you can or like a MIDI keyboard even as well, and actually customize it so you can do some kind of gesture and then have it like you do a Z and it presses the Z key or something on your virtual keyboard, and that does something interesting with your like whatever you've got it connected up to. So that isn't quite working yet, but if hopefully I get some tough enough problems in my main job that I'll procrastinate and spend some more time on that.
Man, I hope for that too. I guess for people that maybe aren't experts in embedded computing systems, could you describe the difference between a Raspberry Pi and an Arduino, and then the sort of different challenges in getting ML to run on a Raspberry Pi versus an Arduino?
Yeah, and at a top level, the biggest difference is the amount of memory. This Arduino Nano BLE Sense 33 is, I think it has like 256K of RAM and either like 512K or something like that of flash, kind of like, read only memory. So it's this really, really small environment that you actually have to run in. And it means you don't have a lot of things that you would expect to have through an operating system, like files or printf, or you're really having to look at every single byte. The printf function itself, in a lot of implementations, it will actually take up about 25 kilobytes of code size just having printf, because printf is essentially this big switch statement of, oh, have you got a percent %f? Oh, here's how you print a float value, and there's like hundreds of these like modifiers and things you never even think of for printing things you'd never even imagine. All that code has to get compiled in if you actually have printf in the system. So all of these devices that we're aiming at, they often have, only a couple of hundred kilobytes of space to write your programs in. So you may be sensing a theme here. I love trying to sort of fit, take modern stuff and kind of like fit it back into something that's like a Commodore 64.
So, okay, it seems like, Pete Warden doesn't always need a practical reason to do something, but what might be the practical reason to use an Arduino versus a Raspberry Pi?
Well, luckily, I've actually managed to justify my hobby and turn it into my full-time project, because one great example of where we use these is I don't see my phone here. I was going to hold up a phone, but you know what a phone looks like. If you think about things like, and I won't say the full word because it will set off people's phones, but the OKG wake word, or the wake words on Apple or Amazon, when you're using a voice interface, you want your phone to wake up when it hears you say that word. But what it turns out is you can't afford to even run the main ARM application processor 24/7 to listen out for that word, because your battery would just be drained. These main CPUs use maybe sort of somewhere around a watt of power when they're sort of up and running, when you're like browsing the web or interacting with it. Um, so what they all do instead is actually have what's often called an always on hub or chip or sensor hub or something like that, where the main CPU is powered down, so it's not using any energy. But this much more limited but much more lower energy um, chip is actually running and listening to the microphone and running a very, very small, somewhere on the order of 30 kilobytes models, ML model, to say, hey, has somebody said that word or that wake word phrase that I'm supposed to be listening out for? And they have exactly the same challenges. You only have like a few hundred kilobytes at most. You're running on a pretty low end processor. You don't have an operating system. Every byte counts, so you have to kind of like squeeze the library as small as possible. And so that's kind of one of the real world applications where we're actually using this TensorFlow Lite Micro. And more generally, the Raspberry Pi is, you're probably looking at, $25, something like that. The equivalent, which the Raspberry Pi Foundation just launched, I think last year, or maybe at the start of this year, that's kind of the equivalent of the Arduino, is the Pico, and that's, I think, like $3 retail. And the Raspberry Pi, again, uses like 1 or 2 watts of power. So if you're going to run it for a day, you essentially need the phone battery that it will kind of, run down over the course of a day. Whereas the Pico is only using like maybe 100 milliwatts, a tenth of a watt. And so you can run it for sort of 10 times longer on the same battery, or you can run it on a much smaller battery. And so these embedded devices tend to be used where there's like power constraints, or there's cost constraints, or even where there's form factor constraints, because, this thing is even smaller than a Raspberry Pi Zero. And you can like kind of stick it anywhere and it will survive being run over and all of those sorts of things.
So can you describe, like, let's take, for example, like a speech recognition system. Can you describe the differences of how you would think about training and deploying if it was going to like the cloud or a big desktop server versus a Raspberry Pi versus an Arduino?
Yeah, and the theme again is size and how much space you actually have on these systems. So you'll be thinking always about how can I make this model as small as possible. You're looking at making the model probably in the tens of kilobytes for doing. We have this example of doing speech recognition, and I think it uses like a 20 kilobyte model. So you're going to be sacrificing accuracy and a whole bunch of other stuff in order to get something that will actually fit on this really low energy device. But hopefully it's still accurate enough that it's useful.
Right. So how do you do that? Like, how do you reduce the size without compromising accuracy? Can you describe like some of the techniques?
Yeah. So I actually just blogged about one trick that I've seen used, but I realized I hadn't seen in the literature very much, which is where, the classic, going back to AlexNet, approach, after you do a convolution in like an image recognition network, you often have like a pooling stage. So that pooling stage, would either do average pooling or max pooling. And what that's doing is it's taking the output of the convolution, which is often the same size as the input, but with a lot more channels. and then it's taking blocks of like 2 by 2 values, and it's saying, hey, I'm going to only take the maximum of that 2 by 2 block, and so take 4 values and output 1 value, or do the same but do averaging. And that helps with accuracy, but because you're outputting these very large outputs from the convolution, that means that you have to have a lot of RAM, because you have to hold the input for the convolution, and you also have to hold the output, which is the same size as the input but typically has more channels. So the memory size is even larger. So instead of doing that, a common sort of technique that I've seen in the industry is to use a stride of 2 on the convolution. So instead of having the sliding window just slide over 1 pixel every time as you're doing the convolutions, you actually sort of have it jump 2 pixels, horizontally and vertically. And that has the effect of outputting the same result as you would, or the same size, same number of elements that you would get if you did a convolution plus a sort of a 2 by 2 pooling. But it means that you actually do less compute, and you don't have to have nearly as much kind of active memory kicking around.
Interesting.
And
I had thought when
yeah,
you said the size of the model, it was just the size of the model's parameters, but it sounds like you also, I mean, obviously you need some active memory, but it's hard to imagine
yeah.
that even could be on the order of magnitude of the size of the model, like literally the pixels of the image, and then the kind of intermediate results, I guess, can be bigger than the model.
Yeah, I mean, well, that's kind of the nice thing about convolution, is you get to reuse the weights um, in a way that you really don't with like fully connected layers. So you can actually end up with convolution models, the activation memory taking up a substantial amount of space. And I guess I'm also getting into the weeds a bit here, because the obvious answer to your question is also quantization, like taking these floating point models and just turning them into 8-bit, because that immediately slashes all of your memory sizes by 75%.
And what about, I mean, I've seen people go down to 4 bits or even 1 bit. Do you have thoughts on that?
Yeah, there's been some really, really interesting work. A colleague of mine actually, again, I'll send on a link to the paper, but looked at, I think it's something about the Pareto optimal, like bit depth for ResNet is like 4 bits or something like that. And there's been some really, really good research about going down to sort of 4 bits or 2 bits, or even going down to sort of, binary networks with 1 bit. And the biggest challenge from our side is that CPUs aren't generally optimized for anything other than like 8-bit arithmetic. Um, so going down to these lower bit depths, requires some advances in the hardware that we're actually using.
Do you have any thoughts about actually training on the edge? I feel like people have been talking about this for a long time, but I haven't seen
Yeah.
real world examples where you actually do some of the training and then it like passes that upstream. Is that
What I've seen is that, especially on the kind of embedded edge, it's very hard to get labeled data. And right now, like, there's been some great advances in unsupervised learning, but our workhorse approach to solving like image and audio and accelerometer kind of recognition problems is still around actually taking big labeled data sets and just running them through training. And so if you don't have some kind of implicit labels on the data that you're gathering on the edge, which you almost never do, it, it's very hard to justify training. The one case where I actually have seen this look like it's pretty promising is for uh, industrial monitoring. So when you've got like a piece of machinery and you basically want to know if it's about to shake itself to bits, because it's got kind of, mechanical problem. And you have an accelerometer or a microphone sensor kind of sitting on this device. And the hard part is telling whether it's actually about to shake itself to bits or whether that's just how it normally like kind of like vibrates. And so one promising approach for this kind of predictive maintenance is to actually spend the first 24 hours just assuming that everything is normal and kind of learning, okay, this is normality. And then only after that start to kind of like look for things that are outside of so you're implicitly labeling like the first 24 hours as, okay, this is normal data. And then you're looking for anything that's kind of like an excursion out beyond that. So that sort of makes sense for some kind of a training approach. But even there, I still actually push people to consider um, things like using embeddings and other approaches that don't require full back propagation um, to do the training. For example, if you have an audio model that has to recognize a particular person saying a word, try and have that model produce sort of an n-dimensional vector that's an embedding, and then have the person say the word 3 times, and then just use k nearest neighbor sort of approaches to kind of tell if subsequent utterances are close in that embedding space. And then you've sort of done something that looks like learning, from a user perspective, but you don't have to have all this machinery of like variables and changing the neural network, and you're just doing it as a post-processing action.
Do you see a lot of like actual real world uses, like actual companies kind of shipping stuff like models into microcontrollers?
Yeah, and again, this is hard to talk about because a lot of these aren't like sort of Android apps and things where people are fairly open and open source. A lot of these are pretty sort of well established old school industrial companies and automotive companies and things like that. But we do see there's a bunch of apps that are already, or a bunch of products out there that are already using ML under the hood. I mean, one of the examples I like to give is when I joined Google back in 2014, I met Raziel Alvarez, who's now actually at Facebook doing some very similar stuff, I believe. But he was responsible for a lot of the OKG work, and they had been shipping. They've been shipping on billions of phones using ML and specifically using deep learning to do this kind of recognition. But I had no idea that they were shipping these 30 kilobyte models to do ML, and they had been for years. And from my understanding, from what I've seen of like Apple and other companies, they've been using like very similar approaches in the speech world for a long time. But a lot of these areas don't have the same kind of expectation that you will publish and publicize work that we tend to in the kind of the modern ML world. So it flies below the radar. But yeah, these things are there's ML models probably running in your house almost certainly right now that are running on embedded hardware.
And I guess besides the audio recognition, what might those ML models in my house be doing? Can you give me like a little bit of a flavor for that?
Yeah, so accelerometer recognition, like trying to tell if somebody's like doing a gesture, or you know if a piece of machinery is doing what you're expecting, like the washing machine or the dishwasher or things like that, trying to actually take in these signals from kind of like noisy sensors and actually try and tell what's actually happening.
You think it's an ML model, my washing machine?
Um, I would not be at all surprised.
Wow.
Yeah.
I guess another question that I had for you, thinking about like your long tenure on TensorFlow, which is such a well-known library, is kind of like how has that evolved over the time you've been there? Like, have things surprised you in the directions that it's taken? And I mean, how do you even think about with a project like that what to prioritize into the future?
I mean, honestly, how big TensorFlow got and how fast was, really blew me away. Like that was kind of amazing to see. I'm used to kind of working on these um, kind of weird technical problems that I find interesting and kind of like following my curiosity. And like I'd been sort of led to TensorFlow by sort of, pulling on a yarn and kind of ending up there. And it was really nice to see. I mean, not just TensorFlow, but PyTorch, AlexNet, all of these other, frameworks. Just, there's been this explosion in the number of people interested. And especially there's been this explosion in the number of products that have been shipping, like the number of use cases that people have found for these has been like really mind blowing. Like I'm used to doing like open source projects which get like 10 stars or something, and I'm like happy because but seeing TensorFlow and all these other frameworks just kind of get this mass adoption has been yeah. I mean, I think it's definitely surprised me and has been really kind of nice to see.
What about like in terms of like what it does? How has that evolved? Like what kinds of like new functionality gets added to a library like that? And why do you make so many breaking changes?
Yes. I would just like to say I am sorry. No, it's really it's such a really interesting problem because we're kind of almost coming back to what we were talking about with Alex, Krzyzewski is like the kind of the classic example of like the ML paradigm that we're in at the moment is you need a lot of flexibility to be able to kind of experiment and create models and iterate on kind of like new approaches. But all of the approaches need to run really, 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 really fast because you're running millions of, iterations, millions of data points through each run just in order to kind of like try out one model. So you've got this really challenging combination of you need all this flexibility, but you also need this like cutting edge performance, and you're trying to squeeze out the absolute maximum amount of throughput you can out of the hardware that you have. And so you end up with this world where you have Python calling into these chunks of these operators or these layers, where the actual operators and layers themselves are like highly optimized, but you're expecting to be able to kind of plug them in to each other in very sort of arbitrary ways and preserve that like high performance. And especially with TensorFlow, you're also expecting to be able to do it across multiple kind of accelerator targets. Things like the TPU, CPUs, and AMD, as well as kind of NVIDIA GPUs. And honestly, it's just a really hard engineering problem. I'm actually, it's been a couple of years now since I've been on the sort of mainline TensorFlow team, and it blew my mind how many dimensions and combinations and permutations of things they had to worry about in terms of getting this stuff just up and running and working well for people. And it is tough as a user because you kind of got this space shuttle control panel full of complexity, and you probably only want to use kind of like part of it, but everybody wants a different.
Right. Well, maybe this is like kind of, I guess, like a naive question, but like when I look at the cuDNN library, it looks like pretty close to like the TensorFlow wrapper. Is that right? Or is there, it seems like it kind of tries to do the same building blocks that TensorFlow has. So I would think with like NVIDIA, it'd be a lot of just passing information down into cuDNN.
Yeah, where I saw a lot of complexity was around things like the networking and the distribution and the very fast kind of making sure that you didn't end up getting bottlenecked on data transfer as you're kind of like shuttling stuff around. And we've had to go in and mess around with JPEG decoding and like try different libraries to figure out which one would be faster, because that starts to become the bottleneck at some point when you're throwing stuff onto the GPU fast enough. And I have to admit, though, I'm getting out of my I've looked at that code in wonder. I have not. I have not tried to fix issues there, so I'm
amazing. I guess one more question on the topic: how do you test all these hardware environments? Like, do you have to like set up the hardware somewhere to run all these things before you ship the library?
Well, that's another pretty like the task of doing kind of the continuous integration and the testing across all of these different pieces of hardware. And all the different combinations of, have you got 2 cards in your machine? Have you got 4? Have you got this version of Linux? Are you running on Windows? Which versions of the drivers do you have? And which versions of the accelerator, the cuDNN, and all of these. There are sort of farms full of these machines where we're trying to test all of these different combinations and permutations, or as many as we can, to try and actually make sure that stuff works. And as you can imagine, it's not a straightforward task.
All right. Well, we're getting close to time, and we always end with 2 questions that I want to save time for. One question is, what is an underrated topic in machine learning that you would like to investigate if you had some extra time?
Well, datasets. The common theme that I've seen throughout all the time I've worked with, I've ended up working with hundreds of teams who are creating products using machine learning. And almost always what they find is that investing time in improving their data sets is a much better return on investment than trying to tweak their architectures or hyperparameters or things like that. And there are very few tools out there for actually doing useful things with data sets and improving data sets and understanding data sets and gathering data set, data points and cleaning up labels. And so I really think, and I'm starting to see, I think Andrew Ng and some other people have been talking about sort of data-centric approaches, and I'm starting to see more focus on that. But I think that that's going to just continue and is going to be, I feel like as the ML world is maturing and more people are going through that experience of trying to put a product out and realizing, oh my God, we need better data tools. There's going to be way more demand and way more focus on that. So that is an extremely interesting area for me.
Well, you may have answered my last question, but I think you're well qualified to answer it, having done a bunch of ML startups and then working on TensorFlow. Like when you think about deploying an ML model in the real world and getting it to work for a useful purpose, what do you see as the major bottlenecks? I guess datasets is one. I agree is maybe the biggest one, but do you see other stuff?
So another big problem is there's this kind of artificial distinction between the people who create models, who often kind of come from a research background, and the people who have to deploy them. And what will often happen is that kind of the model creation people will, get as far as getting an eval that shows that their, model is reaching a certain level of accuracy in their like Python environment, and they'll say, "Okay, I'm done. Like, here's the sort of checkpoints for this model, which is great," and then just hand that over to the people who are going to like deploy it on like an Android application. And the problem there is that there's all sorts of things like the actual data in the application itself may be quite different to the training data. Um, you're almost certainly going to have to do some stuff to it, like quantization or some kind of thing that involves retraining in order to have something that's optimal for the device that you're actually shipping on. Um, and there's just a lot of really useful feedback that you can get from trying this out in a real device that someone can hold in their hand and use that you just don't get from the eval use case. So coming back to like actually Pete Skomorock, and I first met him when he was part of the whole DJ Patil and the like the LinkedIn crew doing kind of some of the really early data science stuff. They had this idea, and I think it was DJ who came up with the sort of the naming of like data science and data scientist as somebody who would own the full stack of taking everything from doing the data analysis to coming up with sort of models and things on it to actually deploying those on the website, and then kind of like taking ownership of that whole end-to-end process. And the teams I've seen be really successful at deploying ML products, they've had people who formally or informally have taken on that hot responsibility for the whole thing, and kind of have the people who are writing the inner loops of the assembly kind of sitting next to the people who are doing the, creating the models. And the team who created MobileNet, Mobile Vision, with like Andrew Howard and Benoit Jacob, like they're a great example of that. They all work very, very closely together, doing everything from like coming up with new model techniques to figuring out how they're actually going to like run on real hardware at the kind of like the really low level. So that's really that's one of the biggest things that I'm really hoping to see change in the next few years, is more people kind of adopt that model.
Well said. Thanks so much, Pete. That was super fun.
No, thanks, Lucas.
If you're enjoying these interviews and you want to learn more, please click on the link to the show notes in the description, where you can find links to all the papers that are mentioned, supplemental material, and a transcription that we work really hard to produce. So check it out.